In this discussion, we explore integer linear programming, a branch of optimization that deals with decision variables that are restricted to integer values. So we will cover the basic concepts of an ILP or integer linear programming problem, including its definition, model components, types, and solution methods, with an example to serve as illustration. So the goal here is for you to appreciate both the mathematical structure and the computational strategies behind ILP. So basically, ILP is a mathematical optimization technique where some or all of the decision variables are required to be integers. In ILP, we restrict our decision variables to whole numbers. This is realistic in many real-world problems. For example, you can't assign 2.5 workers or build half a factory. So there are specific problems that would require whole numbers. Such restrictions make the model more accurate, but also much more difficult to solve computationally. The components in ILP are just the same as that of the LP, except for the integrality condition, which drastically changes the feasible region, since the feasible region of the ILP restricts the feasible region of the LP to consider only integer values. So instead of, for example, if this is the a continuous polygon that would represent the feasible region of the LP. So all points in this region are considered a feasible points. So, but in ILP, we only have a set of if this of discrete feasible points. So we only consider integer values. We don't consider the points in between. So this means that the optimal solution must be searched among these integer points only. So if these are the integer points, we only consider this. We don't consider the points in between. Okay, so there is a linear programming model where the constraint and the objective functions are linear. Then there is also another type of programming model, which is integer programming, wherein the variables and the objective functions are decided to be integers. Now, an ILP is a combination of both. It is a linear programming where meaning the constraints and objective functions are linear. It is also an integer programming because we want the values to be integers. Okay. Now, an ILP can be classified as pure, mixed, or binary. Okay, so a standard ILP has variables that are integers. So an example of that would be work fate allocations or any problem that requires integer values. Now, a mixed ILP, this is the type of ILP wherein we relax it a bit. Some variables are integers while some are not. So an example of that would be production, because sometimes, for example, if you want a kilo of, if we want rice, we can have half a sack or half a kilo, or we can also have them as wholes. Now, a binary ILP is a type of ILP wherein it only takes variables, but variable values. It only takes 0 or 1 as variable values. So this could mean, or this would represent a yes or no or an on or off decisions. And it is common in project selection, and network design problems. Okay, so in some cases, we model ILP directly by declaring the integer variables or the integer restrictions on the variables from the start of the problem. But there are cases when this is difficult to do. So sometimes we first solve the LP version of the problem and then later we enforce the integer values. So this is an indirect approach. And this helps when we want to estimate bounds or we want to test feasibility before applying heavier algorithms. Okay. So in the direct ILP, integer constraints are included explicitly in the formulation of the optimization problem, while in the indirect one, we first formulate the problem, first the LP problem, and then after that we solve the LP, and then we impose integer constraints through additional methods. So in the direct, we model the model specifies which variables must be integers. So explicit integer constraints are already declared at the start of the problem. On the other hand, in the indirect approach, this may not be, the integer constraints or restrictions may not be specified early. So instead of having discrete or disconnected feasible region, we have a continuous LP problem. So common solution methods used are the branch and bound and the cutting planes methods. In the indirect LP, we can also use the branch and bound and the cutting planes after the LP relaxation is solved. So the table here summarizes the differences between IP and ILP in terms of objective function formulation, constraints, type of problems, and the methods of solving. So because ILPs are complex type of problems, we rely on special algorithms. Some of these algorithms would give us exact solutions, while others only give us approximations. So for this lesson, we'll discuss two methods: the branch and bound and the cutting plane methods. So this basically defines the process of solving an ILP problem. So steps 1 to 3 are the basic steps of a linear programming problem formulation, while steps 4 present the method of solving. So the simplest way to approach an ILP is to ignore integrality temporarily. So meaning we remove the integer restrictions first. So this is what we call the relaxation of the ILP. So meaning we relax it. We remove the restriction. So we relax the ILP solution space by removing the integral restrictions. And then after that, after we relax it, we then solve the LP or the linear programming problem, and then the optimal solution of which provides a lower or upper bound for the true integral solution. Now, if the LP solution is an integer, then the solution is also optimal for the ILP, and that means that we are done. Otherwise, we have to use appropriate methods to solve the ILP, meaning we need to look for methods that impose the integral restrictions. Okay, So let us zoom in into step 4.3, the part where the integral restrictions are imposed. So again, as I've said earlier, we'll study two methods, the branch and bound and the cutting plane methods. So these are basically the difference between the two. So the branch and bound divide the problem into smaller sub-problems, and then it uses bounds to eliminate invisible solution, while on the other hand, the cutting plane method adds linear constraints to eliminate the fractional solutions while preserving the feasible integral solutions. So basically, the branch and bound method systematically explores the feasible solution space, and then we branch on fractional values, and then we bound using, or we impose bounds using LP relaxations. Now, this creates sub-problems, and then these sub-problems are pruned as soon as we confirm that they can't produce better integer solutions. Okay, so this is a summary of the branch and bound algorithm, but I think it's better if we demonstrate it through an example. So recall the classic Landowing problem. For this problem, the LP relaxation gives fractional results. So here. Okay, so we'll implement the branch and bound method on this. So meaning we will see how successive branching identifies the best integer combinations for x1 and x2. Okay, now let's study the visible region. The lattice points, or these dots here, are the elements of the solution space of the ILP because they're integral values. Now, if we join them with a shaded region, that's when we create the solution space of the LP, meaning the linear programming problem. Now, the optimum solution is obtained by removing the integer restrictions, meaning we consider the whole space. So again, if we solve the LP, we know that the solution is this point here, which is the intersection of the two constraints, giving us x sub 1 equals 3.75, x sub 2 equals 1.25, with objective function value equal to 23.75. Okay, so these values give the LP upper bound for the original maximization ILP problem. The true integer optimum can, so this means, since this is the upper bound, it means that the true integer optimum cannot exceed 23.75. Again, the solution of the LP gives us an upper bound for the solution of the ILP. So this 23.75 was the solution of the LP, meaning the relaxed problem. So meaning the solution of the ILP should not go bigger than this. Okay. Now, how do we implement the branch and bound? Now look at this. So since 23.75 is not an integer, then this already tells us that branching must be done. Okay. So meaning, okay, so this is how it goes. The first one, the solution of the ILP, of the LP or the ILP relaxation, we label it as LP1. So that's the first branch. Okay. Oh, that's the original. Basically, let's say branch sub-0. Okay. Now, if let's decide on a branching variable. So let's decide that our branching variable is x sub 1. You can also do x sub 2. Okay. But for the sake of discussion, let's assume, without loss of generality, we assume x sub 1 as the branching variable. So x sub 1 is 3.75, and 3.75 is between 4 and 3. Okay, so meaning if we remove this, we are, when we only think of integers, so meaning x sub 1 can be greater than or equal to 3, and x sub 1 can also be less than or equal to 4. So this creates the branching. So the first branch, which is labeled as LP2, refers to x sub 1 less than or equal to 3. And if we solve this problem, we get x sub 1 equals 3, x sub 2 equals 2, and z equals 23. So this point is integer fitable. This one. This is integer fitable. So we have a candidate integer solution with value z equals 23. Now these sets are incumbent or best known integer to 23. Okay, so at this point, the best known integer is 23. The LP bound for this branch is 23, meaning this branch cannot produce a better integer solution than 23. Okay, so to verify the result, let us set x sub 1 to be equal to 3. Well, this is okay or acceptable because for this branch, x sub 1 can be any number less than or equal to 3. Now, consider the first constraint. The first constraint was x sub 1 plus x sub 2 less than or equal to 5. So if we substitute x sub 1 equal to 3 there, we get x sub 2 less than or equal to 2. From the second constraint, which was 10x sub 1 plus x sub 2 less than or equal to 45, we get x sub 2 less than or equal to 2.5 when we substitute x sub 1 equals 3. So from this, from the two restrictions on x sub 2, we have x sub 2 less than or equal to 2 and x sub 2 less than or equal to 2.5. We can, or it is safe for us to assume or to take the value of x sub 2 equals 2. So here we have x sub 1 equals 3 and x sub 2 equals 2. The fitable maximum value for this would be 23, which is an integer. Okay, so we just verify this value. So what does this mean? This means that, again, as what I've said earlier, this point here, the point represented by this, is integer fitable. Again, meaning that we have candidate integer solutions with optimum value equal to 23. And since these are, remember, if the LP solution, if the solution is an integer, then that probably is then that would be the solution to the ILP. So for this branch, since we found integral values, then we can conclude that this is the solution of the ILP, or the optimum solution of the ILP at this branch, and this tells us that we couldn't find any more better solution than, or better value than 23. Okay. Okay, now since the LP2 branch is already optimal, then we can't do anything about it anymore, so we have to check the other side, or the LP3, which refers to x sub 1 greater than or equal to 4. Okay. So if you look at this, if we're looking at this, we add another constraint to our problem. So we have the first constraint, the second constraint, and then we added x sub 1 to be greater than or equal to 4, and x sub 2. Yeah, this one is already, it's the non-negativity constraint. So we added this. Okay. So when we solve this LP with x sub 1 equal to 4, the same with what we had in the other side earlier in LP2, we substitute x sub 1 equals to 4 to the first constraint, which gives us x sub 2 equal to 1. So if we check the second constraint, we substitute x sub 1 equals to 4 there, we get 5 over 6 or 0.83. So if we take these values, we have x sub 1 equals 4 and x sub 2 equals 0.83. This gives us an objective function value of 23.33. Okay, so let's look at this. Originally, we had, when we relaxed the LP, we had 23.75 as the optimum objective function value from the LP relaxation. Now, the objective function value for LP2 is 23, which is an integer that is smaller than the one we got from LP1. It is also smaller compared to LP2, to LP3. So this verifies that LP2 gives us the lower bound for the true optimal solution. LP3, on the other hand, gives us an upper bound for this branch. But this LP3's best possible integer solution has to be less than or equal to that of its LP relaxation. Okay. Now, since we desire that the objective values are integers, then the best integer solution in LP3 must be an integer that is less than or equal to 23. So this means that for LP3, we have z equals 23.33 and must be less than or equal to 23. So what's the problem with this? This would not be able to give us a better integer solution. So this means that we can disregard LP3 and focus on LP2. Okay, so in this case, we say that LP3 is fathom or pruned. Okay, so what does fathom mean? A branch is said to be fathomed when it cannot yield a better integer solution than the current best, meaning wala nang improvement. So when this happens, it is best to stop exploring that said branch. Okay, so after branching, LP2 provided us a feasible integer solution with z equals 23, which becomes the current or the incumbent. Now, the LP relaxation of LP3 gave us 23.33, but this upper bound cannot lead to an integer solution exceeding 23. That was why we said that it was fathom. Okay, now since there are no other branches that remain to be explored, then the integer solution from LP2 is the optimal solution for the ILP. So graphically, the branch and bound method is implemented using this. So again, we have the solution space, and then we first defined that we branch using x1. So meaning we assume that there is, okay, so at this point we assume that there is an integer, let's say x hat, between 3 and 4. Okay, why between 3 and 4? X1, if we focus on X1, X1 is somewhere here. So we assume that there is an integer between 3 and 4 such that that integer x hat would satisfy the problem. But the problem is there is actually no integer between 3 and 4. So we have to delete this space between 3 and 4. So that's why we get this. This is the deleted space. Okay, the removal of that space gives us two disconnected spaces. That's why we had branches. So we have this branch which is defined by x sub 1 less than or equal to 3. This was LP2. And then we have another branch which is x1 greater than or equal to 4, which is LP3. Okay, so yeah, so we created these two branches, LP2 and LP3. So we were able to do this because having no integer values between 3 and 4 gives us a guarantee that no ILP fitable information is lost. Again, what did we say? We were able to remove or to branch out by removing this space here because we know that removing this does not harm our fitable region, because remember, we are only concerned of the integral values, and since we found no integers between 3 and 4, then it would be safe to remove this part without sacrificing our integer feasible solutions. Okay. Now graphically, if you focus on LP3, you can see that it does not provide a space for the solution to improve. That's why it was considered phantom, meaning we can disregard it and focus on LP2 instead. So we already know that LP2 gave us an integer solution which is better among the branches. Thus, the solution from the LP2 is optimum. Now, the cutting plane is a method that iteratively tightens the fitable region by cutting out invisible regions of the ILP from the fitable region of the LP. Okay, so how do we do? Okay, now each cut slices away fractional parts of the fitable region while keeping all integer fitable solutions intact. So it was like the graph from earlier, but this time, each cut represents an additional constraint. Okay. So if you're using the simplex tableau, we call them Gomory cuts, or if we use algebraic manipulation, they're called Schwatal Gomory cuts. So let's see how this works. Okay, so intuitively, again, we solve the ILP first using our LP. So when we solve the LP relaxation of the ILP and we get fractional values, it tells us that the feasible solution space is too large. Again, why is it too large? Okay, so if this is the feasible solution space, what we wanted are just the lattice points, the integer values, but since we got fractional values, it means we got points somewhere in between these integers. So that's why it was too large. It was not restrictive. Okay. So what we do is we cut the plane or this solution space because we want to remove the fractional optimal solution. But we also want to keep all integer feasible solutions and we want to maintain linearity. Okay, now these cuts are not randomly generated restrictions. Okay, so these cuts are designed to improve the solution space. So you can think of it as a way to sharpen or improve our solution space that will lead us to identifying integral solutions. Okay, so we add a cut when the LP relaxation gives us an optimal solution, and this solution contains fractional values. If there are no fractional values, then we don't need to do this. Okay. So again, let me emphasize, we only apply a cut once we see that the LP optimal point is fractional. If the LP relaxation gives us an integer value, then we are done. We don't need to do anything. But if fractions appear, that's when we surgically, parang we're doing an operation, we surgically add a new constraint. It's like saying this fractional point is impossible for the real problem. So we'll have to mathematically forbid it while still allowing all legitimate integer options. Okay, so to create a cut, we only manipulate existing valid constraints. Okay, so let's look at this problem. So how can we do that? So look at the second constraint. Remember, we only manipulate valid existing constraints. So, okay, why the second constraint? Because this one is simple already because the coefficients are 1. But the second constraint, the coefficients are even numbers. So we can divide it by 2. Now when we divide it by 2, we have 5x sub 1 plus 3x sub 2 less than or equal to 22.5. So this side, we get integers, but the problem is this side here is not an integer. So we have x sub 1 is an integer, x sub 2 is an integer. The coefficients of these variables are integer. So basically, this is a linear combination of integers, which should also give us an integer. Now this is contradicting because the restriction here is not an integer. Okay, so what can we do from there? So we can safely, so it allows us, so it tells us that we can safely tighten this inequality. Remember, it was 22.5, so we can tighten it and say, and to the nearest integer, and say that now our new constraint 5x sub 1 plus 3x sub 2 is less than or equal to 22. This excludes fractional solutions like 3.75 and 1.25. But we accept, or this allows us to accept integer options. So with this new revision of constraint 2, we were able to construct a new LP. Okay, so the new the added constraint, we call this the first cut. So once we add the cut, we solve the LP again. So we add a cut, meaning we added a new constraint. So we're restricting the solution space based on this constraint. And then we solve the LP again. The fractional point should no longer be available with this new constraint. And the new LP optimum is expected to be closer to the integer area. Okay? So we repeat the streaming process only as needed. So when the LP finally outputs an integer solution, then that should be a signal for us to stop, meaning the optimal solution is for the ILP is already found. Okay. So we will now solve this new LP. Okay, so new LP, it was the same with the original with a new with an additional constraint, which was the first cut. Okay, so this is the fitable region. Now the orange broken line represents the new constraint. Okay, so check the candidate corner points. So our candidate corner points, we have 0, 0, and 0, 5. So with this, okay, so when we check that, we check the intersection of cut 1 with the first constraint. So cut 1 and the first constraint. So from the first constraint, we have x sub 2 equals 5 minus x sub 1, and then we substitute this to the equation of cut 1, which gives us x sub 1 equals 3.5, x sub 2 equals 1.5, and z equals 23.5. So it still yield fractional values. Okay. Now let's see cut 1 and x sub 2. So if x sub 2 is 0, we substitute it to cut 1. Then we get x sub 1 equals 22.5 or 4.4, and then x 2 0, and z is 22. Okay. Now, to eliminate the fractional point that we got earlier, we look for combinations of the original constraint that yields a fractional right-hand side, and then we floor the right-hand side to produce a valid integer inequality. Okay, so there are many ways to do this. So one way is to subtract. So you have to study the problem well. So one way is to subtract constraint twice. Okay, we subtract twice of constraint 1 from constraint 2. Okay, so constraint 2 is 10x sub 1 plus 6x sub 2 minus twice of constraint 1. So this gives us, manipulating this gives us 2x sub 1 plus x sub 2 less than or equal to 8.75. Now, if we take the floor of this, it would yield 2x sub 1 plus x sub 2 less than or equal to 8. And this cut excludes 3.5, the point 3.5 and 1.5, while keeping the point 3, 2. So therefore, this is a legitimate cut. Now, for the integer values of x sub 1 and x sub 2, we can tighten. So this one was what I've said earlier. If we tighten this, we get this. Okay. Recall what we had earlier. Was this, right? And 8.5 is greater than 8. So this means that the old fractional solution was taken out of the feasible region. The old fractional solution was 3.5 and 1.5. So since it yield 8.5, which is greater than 8, it means when we tightened the solution space, it expelled this fractional solution out of the feasible region. So meaning the cut was effective. It was able to exclude the fractional solution. So if you notice, our new LP has two cuts or two additional constraints. The first one was simplifying the second constraint and restricting the right hand side to be the nearest integer, while the second cut was from a linear combination of the existing constraint. So we have this. Now this third one, no, this second cut is defined by the green line, the green broken line. So let's verify this. So check the intersection of constraint 1 and cut 2. So what we see is we are able, or it gives us an integer value. X sub 1 is 3, x sub 2 is 2, and z is 23. Z equals 23 is an integer. If we check other candidate corners in the visible region, you can see that no other corner yield higher integer objective function values, meaning there are none of these gives us something higher than 23. Okay, now what does this mean? This means that when we added the second cut, we were able to find the optimum solution, which was x sub 1 equals 3 and x sub 2 equals 2. So all in all, adding two more constraints to the objective function helped us restrict the solution space to remove the unnecessary fractional fitable solutions, and they also led us to finding the optimum integral solution. So that is what cutting plane method is. So again, the branch and bound, we branch on the fractional values and then we impose bounds. Also, we use bounds to impose on integral solutions, while the cutting plane method is we add more constraints so that our existing LP would become more tight. Meaning, when we say tight, is meaning we remove the fractional values while we keep the valid integer values. And this ends the presentation.